Hello, because my laptop has decided to die in a ball of fire, I'm recording this in a slightly different way. So let's do the calculation. I've written down a couple of variables I haven't quite finished because laptop decided to die in a ball of fire, hence me having many issues to do with trying to get this video completed. It's approximately 11:30 now. This is supposed to go at 1:45. God help me. So we've got mass is 1.7 because we know that's the pumpkin. Then rho is 1.225, which is the density of air. Then area is pi r squared, which is pi over 100. For reasons that should be pretty clear, you've got a pumpkin. Oops, that's big. And you have the radius being 0.1 meters, which is 10 centimeters. And then you can square it, which gets 1 over 100 times by pi. And you get the area of the circle. And the area of this circle is bigger than the area of this side. And that's not working anymore, but don't worry. And then sigma is 0.3. And the gravitational constant is 9. Oops, this is not working, 9.81. So, we can calculate terminal velocity pretty easily by going v of t, which is plugging all the numbers into the formula we had earlier, which is 2 times 1.7 times 9.81, all over 1.225 times pi over 100 times 0.3 times to the half, which is approximately 53.74. Brilliant. Now we can kind of look at the pumpkin flying through the air. To do this, we're going to draw a quick diagram, which it looks like this. Which we're going to start at a height H, and then that's the pumpkin. And then we've got a maximum, then we've got here, which we're going to call R, and then this is X, so T on 2, you'll see Y in a minute, and we're going to call this big H. So, also, it goes, that's the angle alpha. Alpha is just a Greek letter, and that's a velocity V. What I've drawn here is a side-on portrait of the pumpkin flying through the air. I don't have any oranges, but we have green. Yeah, that's the floor, or the kind of the grass along the floor. And then we have the sky up here. We'll indicate that by blue and green axes. Right? Now we can look at these axes and say, okay, we know there's functions to do with the position with respect to the x-axis, which is this one, and with that one with respect to time. So we know that the pumpkin is in the place v cos alpha at time t, and also we know that alpha is going to be 45 because 45 degrees is the most optimal angle to chuck something. And we know we've got a y of t, which is v t sine alpha minus gt squared on 2. Now, we want to look at velocities because we're talking about terminal velocity. So we can create new functions. V of x of t is equal to v cos alpha from this one by differentiating. Don't worry if you don't know what that means. And vy of t being v sine alpha minus gt. Right, we're going to evaluate these functions at a point here, just before you hit the ground. But it's close enough to the ground that we can use the time equal to v root 2 on g, which is the total time in flight. And we can say that because we're going to take it close enough, so mathematics says if it's close enough, it is. Yeah, just using an approximation. Yeah, with a sip of my coffee, give me a second. I don't know if you can hear that, but anyway, right. So, if we evaluate them at that point, we can then multiply them by themselves, you square them, and then add them together, and then make them equal to the velocity. Because the actual velocity at this point is vt, but vt is a number, and it's not in any sort of direction. But these Vx and Vy, they're in kind of a direction. So Vx is the velocity in this direction, Vy is velocity in this direction. So we know that V is equal to the root of Vx squared plus Vy squared. And at that point, V equals Vt. So if we, I'm trying to work out how to do this now. There, move the camera. We can then do a bit more calculation. So V of x, Vx of t is equal to V times root 2 on 2, which is cos of 45. I should probably write that out. And Vy of t is equal to V sine 45 minus gt. But t is our V root 2 on g. The wonderful thing about cos 45 and sine 45 is they're the same. So that is just V root 2 on 2 minus bang bang V root 2, which is minus V root 2 on 2. Okay, so now we can calculate big V, or big V, but V, which is the squares of them. So it's V root 2 on 2 squared plus V root 2 on 2 squared, negative, and take the square root of that, and then that's equal to 2v squared on 4 plus 2v squared on 4, which is the root of v squared, which is v. So therefore v of t is v. So the original velocity, which is v here, this is our terminal velocity. So now we can calculate what, well, just for fun really, for what v, well, h is, h here, what this h is, and what the range is. So that's what the question was asking. It was kind of, well, what the speed, which we had here, our terminal velocity was the speed, and then it asked, well, really, where are we? So what's r? And we can do that quite easily by knowing that, which is equal to 53.74. And we've got equations for both of these. So big H is v squared sine squared alpha over g, which is 53.74 times by root 2 on 2 all squared all over g. Okay, good stuff. And then that is 73.54 meters, well, approximately. And we can calculate the range, which is how far we were. I'm going to warn you before I calculate this number, it's not going to be that impressive because we've got a very small pumpkin, which is 53.74 sine of 90 over g. Oh, sorry, there's 2g there. I've missed a 2g, which is 294 meters, 0.39. So if this pumpkin that I have, as I showed you earlier, was hurling towards you, and it was travelling at its terminal velocity, you would be about 300 meters away from the machine that's pelting it. But they use bigger pumpkins, and the terminal velocity of an object increases quite rapidly with its mass. So if you had a bit more mass, then it would be travelling quite a lot more. And yeah, that's it. Thank you very much for watching my piece. I'm James. Well, I left James A, but I'm James. You can find me anywhere under I left James A. And thank you very much. Bye.